right, this is our last set of tests before we have our 9196 test. So there are two tests to talk about called the ratio and the root tests. And they have very similar stipulations. And I want to make a note up here in the corner. Both of these tests take a series. Let's look at some of our examples. They take a series that might involve factorials, exponentials, something that's not truly geometric, not truly a p-series, and they basically compare series to geometric series. What do I mean by that? Let's look at this first ratio test. So let's let, I'm just going to call this series A, be a series with non-zero terms, and let the limit as n approaches infinity of a sub n plus 1 divided by a sub n, the absolute value of that, let it equal L. Let's pause and talk about what that is saying right there. A sub n and a sub n plus 1, those are, we're talking about terms in the sequence. So this is saying, how do I want to say this? This is saying like the next term divided by the previous term. Remember when we were learning geometric, I said, well, if you're looking at a series of terms like 1 plus 1/10 plus 1/100th plus 1/1000th, if you're looking at a string of terms like that, you can decide if it's geometric by just dividing consecutive terms. That's what I'm trying to say here. The next and previous thing, I don't know if that's quite fitting or not, but if you divide the second term by the first term, and that ratio comes out to a number at infinity, then there are three different scenarios. If that number is less than 1, then your series will converge, and it will converge absolutely. Now think about that. Why does it converge absolutely, first of all? When we're taking the absolute value, if we can show that the positive series converges, then the alternating series would converge too. But why does it matter that it's less than 1? Think back to the geometric series. If the ratio you have raised to a power is a fraction between 0 and 1, then your geometric series converges. And we're kind of saying the same thing. This is not geometric, but if the terms divide out to some sort of fixed ratio in the long run, then it kind of behaves geometrically, I guess you could say. Now, if that ratio comes out greater than 1, then the series will diverge for the same reason that a geometric series diverges. The terms are just getting bigger and bigger and bigger. The ratio between whatever you divide this term divided by its previous term, that keeps getting bigger and bigger and bigger. So the sum's going to keep growing. If it's exactly equal to 1, now geometric series would diverge. Here the test is inconclusive. So we would have to go to something else. Maybe we would have to do, maybe we could do a limit comparison test, or maybe we'd have to get into like a ratio test, an integral test or something. But this ratio test is usually, can't spell, oh my goodness, usually used with factorials. So like when in doubt, if you see a factorial, maybe try the ratio test. And it's often on free response, FRQ. This is another one of those tests that can tell us whether something converges or diverges, but it does not tell us what the series converges to. All right, so let's look at the first test. What do we have to do here? I notice there's a factorial, and this thing isn't alternating, it's not geometric or any of that. So the first thing I want to do is look at the limit as n approaches infinity of a sub n plus 1 divided by a sub n. What's a sub n plus 1? It's 2 to the n plus 1 over n plus 1 factorial over a sub n, so just the original 2 to the n over n factorial. Now this is the only time I'm going to write this complex fraction like this. For every other problem, I'm going to go straight to my next step, which is to get rid of that craziness and just write it as 2 to the n plus 1 over n plus 1 factorial. Let's just get straight to multiplying by the reciprocal of this. n factorial over 2 to the n. Now, way back in the beginning of the chapter, we talked about canceling factorials, and we're going to need that skill here. So back when we were looking at just sequences, n factorial and n plus 1 factorial. Remember, n plus 1 factorial, if you want to write this somewhere, is n plus 1 times n plus 1 minus 1, so times n minus 1 times n minus 2, etc. N factorial is n times n minus 1 times n minus 2, etc. So these two factorials cancel. Everything cancels except for the n plus 1 that would be left over. All right, so that cancels. 2 to the n plus 1 divided by 2 to the n, you subtract your exponents. N plus 1 minus n is 1. So to clean this up here, I have the limit as n approaches infinity of 2 over n plus 1. That's all that's left when stuff cancels out. 2 over infinity is 0. We just got a limit that's less than 1. Therefore, the series converges. And it does converge absolutely, but I'm just going to write converges by ratio test. The absolutely piece, again, is really just if you have something that's alternating, we're showing, if we're showing that the limit of the positive term is approaching a value less than 1, then this converges, whether it's alternating or not. Okay, so for number 2, again, I see factorials. So the first thing I'm going to try is this root test. Let's go with not writing the complex fraction. Let's start on the second step. So plug in your n plus 1s. N plus 1 factorial over, now when you plug in n plus 1 here, it's 2 times n plus 1 plus 1 factorial outside of all of that. So it's really 2n plus 2 plus 1, 2n plus 3 factorial. All right, and then what do we have? Times the reciprocal of this. So 2n plus 1 factorial over n factorial. Now we have to look at what cancels. 2n plus 3 factorial is 2n plus 3 times 2n plus 2. Because remember, the definition of a factorial is whatever you have minus 1, and that number minus 1, minus 1, minus 1. So anyway, times 2n plus 1 factorial. It'll keep going. So the 2n plus 1 factorials cancel. N factorial cancels with n plus 1 factorial to leave you with n plus 1. So for our notes, I'm going to write this a bit nicer. And I suppose I would on the AP test too. But like when you're doing homework, it makes sense to me to just kind of cancel like I'm doing here. Anyway, it needs to be clear to you what you have left. I have a bottom-heavy rational expression here, right? An n over a 4n squared. So that limit is equal to 0 as well. Maybe I should make a note here. In the first one, 0 is less than 1. Same here, 0 is less than 1. Therefore, the series converges by the ratio test. All right, let's look at number 3. 2n squared minus 1 over 2 to the n. All right, so if I look at before I dive right into the ratio test, this is not just geometric. And if I tried to compare it to 1 over 2 to the n, n squared minus 1 would be bigger than 1 over 2 to the n. So that's not really going to help me with my comparison test. So anyway, I can try the ratio test. All right, so I need to plug in n plus 1 and square it, and then do minus 1 over 2 to the n plus 1, and then multiply that by 2 to the n over n squared minus 1. And let's see what we have. We would have the limit as n approaches infinity of what? This is n squared plus 2n plus 1 minus 1. This 2 to the n cancels with 2 to the n plus 1 to leave you with 2 to the first. So there's a 2 down there. Then you still have n squared minus 1. There's no real reason to factor and simplify this. I can see that this is a tie. So its horizontal asymptote would be 1/2. 1/2 is still less than 1. So this behaves like a geometric function that has a ratio of 1/2 in the long run. That's all that that's saying. In the long run, eventually, the ratio of your terms is going to be very close to a constant ratio of 1/2. So therefore, this series converges by the ratio test. So again, this is just saying if I were to expand out, let's say, thousands of terms, by the time I get out there toward the end and I divide consecutive terms, they're pretty much going to be dividing to 1/2, which is pretty much geometric. Okay, another factorial. So I'll dive right into my ratio test. If I plug in n plus 1, there are n's everywhere here. N plus 1 to the n plus 1 over n plus 1 factorial times n factorial over n to the n. All right, how do we work this out? Well, we can at least cancel the factorials, right? N factorial, and that'll just leave me with n plus 1. Now, I have the limit as n plus 1, the limit as n approaches infinity of n plus 1 to the n plus 1. I guess I could rewrite that a little bit if it helps. Like I could write n plus 1 to the n times n plus 1 to the first, or just n plus 1, over n to the n times n plus 1. Those n plus 1s cancel out, right? But now I have n plus 1 to the n over n plus 1 to the n. That is a tie, right? As you get out toward infinity, this plus 1 is awfully insignificant. So I pretty much have 1. So my test is inconclusive. It doesn't mean the problem is unsolvable. It means I need to rework or keep working on the problem. Well, what if these are both to the n power. So what if I take it down here and say, let's write this as n plus 1 over n to the n power. That by itself doesn't really get me anywhere, but how about one more step? Let's divide each term by n. N divided by n is 1. 1 divided by n would just be plus 1 over n. Raised to the n power. This is one of those like, hey, this looks like a compound interest type formula. Oh yeah, the limit is e to the a times b. A is the value in the numerator. B is the value being multiplied here. E to the ab is e to the first. Now, in this case, I got a number. E to the first is greater than 1. Therefore, this series diverges by the ratio test. We just showed that way out toward infinity, if you start dividing consecutive terms, their ratio is going to be e. And that means that you're going to be raising like e to a power, and that's just going to keep growing without bound. All right, example 5. Now this one's alternating, okay? So let's see, could I just do alternating series test? Because I don't always want to dive into ratio test. If I see something alternating, I like to kind of run through my alternating checklist. Is this alternating? Yep. What about the nth term test? Does it pass that? Now, if I'm working on multiple choice, I'm going to think about function races and the fact that n to the first grows faster than square root of n. So I know that this does come out to 0. If I'm in a free response question, I should probably do a round of L'Hopital's that's going to show this denominator derivative becoming 1, this becoming, 1 over 2 radical n, and then that's how I show my limit 0. But just for our notes, I'll just say 0, okay? And then finally, are the terms actually decreasing? Square root of n plus 1 over n plus 2, is that going to be less than or equal to square root of n over n plus 1? If you're not sure on that, You could plug in some numbers and kind of make sure. If you were on a calculator part, you could check with your calculator. You could really cross multiply if you wanted to double check. But I'm going to say if I think about square root of n over n plus 1, again, those terms would need to be decreasing. Like, how could I all of a sudden get a bigger number? All right, so if all three of those things are satisfied, then I could say this converges by the alternating series test. What if I would have tried the ratio test? If I would have tried the ratio test, I'm just going to make a note of this. You can try it on your own if you want to. The ratio test gives us limit equal to 1. So we would have had to go back to the drawing board and do this. All right. Follow up on this. So we just showed that the alternating series converges. Does the positive version of that series converge or diverge? And how could we tell? So now when it's not alternating, I might want to compare it to something. I might want to say, well, I can compare square root of n over n plus 1 to what? What if I just compare it to 1 over n? What do I know about that? Well, n plus 1 is just a slightly bigger denominator, so there's not a huge change there. But having a square root of n, as you head out toward infinity, that's going to be way bigger than 1. So this fraction is definitely greater than or equal to 1 over n. And I know that harmonic series, 1 over n, that diverges. And since it's the smaller of the two in the comparison, it's pushing up and forcing the other one to diverge as well. So that series diverges. All right, well then what does that mean? It means that, sorry, I'm going to make a note. Diverges by direct comparison test. What conclusion can you make about that alternating series? So not only does it converge, I can say that it converges conditionally, not absolutely. That series only converges because it's alternating. Otherwise, it would diverge. All right, what about the root test? Notice that the conditions about the limit are the same. If the limit's less than 1, the series converges. If it's greater than 1, diverges, equals 1, inconclusive. What does this root test say? So you're going to have some sort of series that's some sort of expression raised to the n power. And the expression will often have an n within it, so like an n to an n. If you can take the nth root of something to the n power, so essentially you're just left with the a sub n part, if you can figure out what the limit of that is, then we can follow these rules and say, oh, this thing that's inside being raised to the n power, in the long run, it behaves geometrically again. All right, so we're just kind of comparing it to a geometric series. So let's look at this example. It's e to the 2n over n to the n. So first of all, let's rewrite it. So we have something to the n power, a single thing to the n. That would be e squared over n, all raised to the n power. All right, so if we do that, I can't say geometric because remember, true geometric series do not have variables in them. So I shouldn't have put equals there, sorry. So the next thing I want to do is look at the root test. The root test says just take the limit as n approaches infinity of the nth root of this expression. The nth root of something to the n is just the thing in parentheses. That's why we take the time to look at that. The limit as n approaches infinity of e squared over n is 0, and 0 is less than 1. So therefore, this converges by the root test. The difference between the root test and the ratio test, the root test, I can rewrite this whole thing to the n power, and the ratio test, sure, some things are written to the n power, but not everything, numerator and denominator, had a power of n on it. That's the difference. Number 2, a whole big thing raised to the n power. All right, so let's look at, so I don't have to rewrite it, I can get right to the limit. The limit as n approaches infinity of n squared over 3n cubed minus 6n. That's bottom heavy. Its limit is 0, less than 1. Again, converges by root test. All right, so let's kind of do a summary of things we should be looking at. So the first thing you want to do when I throw all this at you, all different kinds, is mentally check nth term test. And I'm going to write for divergence, because on that first quiz, some of you were telling me things converged by the nth term test, and that's no good. All right, and then the next thing you do is just check, like, is this one of the recognizable ones, I'll say. I don't want to call them easier ones, but recognizable. Like, is it a P series? Like a nice pure P series? Is it geometric? Maybe there's a good telescoping or telescoping type. Okay, so that would be one of those. Or, you know what, let's throw alternating series in there too. Anytime I see -1 to a power, I check that alternating series because that's nice and quick. Remember, that one's only for convergence. If it's not recognizable, can you make some sort of comparison? Like, does it look very close to one of these recognizable ones so that I can just do direct comparison test or limit comparison test? If it's not one of those, then maybe it's a ratio test. Like, are factorials involved? Or maybe it's a root test. A bunch of things to an n power, like a whole fraction to an n. If I've exhausted all of those options, then I'll begrudgingly do integral test, as long as the terms are positive, decreasing, continuous. All right, so our task is to try to tackle these problems and figure out what test are we supposed to use. Mentally check the nth term test. Are these terms approaching 0 so that I should even bother seeing if it converges? That is a big no. The limit as n approaches infinity of n plus 1 over 3n plus 1 equals 1/3. This series diverges by nth term test. All right, up next. A nice simple little constant to the n power. That looks geometric to me. R is pi over 6, definitely less than 1. We need to review this from our quiz. We are not starting at the 0 term. We are starting at the a sub 1 term. So not only do I know that this one converges, but I can tell you what it converges to. So I can say, oh, it converges to that first term over 1 minus r. And if I multiply everything by 6 to get rid of that ugliness, I can say, oh, that's pi over 6 minus pi, right? I think so, yeah. And then converges by geo series test. Let's make a note. Which tests give me an actual sum? P series does not. P integrals did in chapter 8, but geometric gives me a sum, telescoping gives me a sum, and that's it, right? Only two that give sums. Okay, anyway, what about this one? Let's see. Ooh, this is n times e to the negative n squared. Run through. It's n over e to the n squared. So yes, it passes our little nth term test. It could converge. Not a p-series, not geometric, not telescoping, not alternating. I have nothing good to compare it to. There are no factorials, so it's probably not a ratio test. Can't take the nth root of anything. Down to integral test. Let's do a quick check. Are the terms positive? Yeah, you're plugging in 1 over e to the, or n over e to the n squared. Are they decreasing? Yes. Are they continuous? Yeah. So integral test it is. Change colors so I don't mess things up. So this would be, I'm going to put in my limit notation right away. Limit as b approaches infinity of the integral from 1 to b of x e to the negative x squared dx. I think this is a nice little u sub, right? U is negative x squared. Du is negative 2x dx. I need a negative 2. Toss in a negative 1/2. So now we have it as e to the u du. Now, in interest of space, I'm going to kind of illegally plug in my b right away. All right, so what am I looking at? I've got negative 1/2, and then I've got e to the u, but remember, u is negative, a negative exponent, so I really should write this as negative 1/2 times 1 over e to the x squared. So that, oh, I said I was going to plug in my b. Well, anyway, I'm going to just go ahead and do the limit in the next step. So when I do this, I get negative 1/2 times 1 over infinity. So that's 0. Minus negative 1/2 times 1 over e. The point is that I'm getting a number, 0 plus 1 over 2e. This is not what the series converges to, but the series does converge, because I got a number, by integral test. All right? Hopefully that's our only integral test, right? 1 over 3n plus 1. Oh, it's so close to that harmonic, and it's kind of that general harmonic that we were looking at. So I should probably just go ahead and compare this. So let's compare 1 over 3n plus 1 compared to 1 over n. Definitely less than. Technically less than or equal to, but you can just write less than, whatever. What do we know? We know harmonic series diverges. Now remember, the bigger series is diverging. That does not help me. I can't use direct comparison test, but I can hop over to limit comparison test. The limit as n approaches infinity of my unknown over my known. 1 over 3n plus 1, unknown. Instead of divided by, I'm going to say times the reciprocal of my known. That's 1/3. Remember what we're saying with the limit comparison test is, oh, I got 1/3 instead of 1 this time. That's exciting. As long as I get a number, then these two series act together. It's kind of confusing with all our different limits now. So anyway, I got a number. These two series act together. Since my known series diverges, my unknown series diverges by LCT. Definitely something to study before this test is like what the rules are for, what the differences in the rules are for ratio and root tests now that we know them, compared to compared to limit comparison test, because it's different. All right, I see something alternating, so I'm going to try alternating series test. Is this alternating? Yep. Are the terms, or I'm sorry, check the nth term test. Are the terms approaching 0? Yes, they are. Are the terms decreasing? 4n plus 1 would be 4n plus 4 plus 1. That's definitely less than or equal to 3 over 4n plus 1. Yep. So this series converges by alternating series test. We don't know what it converges to. It will never diverge by alternating series. If I get a number here, it other than 0, then I would say diverges by nth term test. a factorial is involved, we should probably try the root test. So set up the limit as n approaches infinity of n plus 1 factorial over 10 to the n plus 1 times, flip this fraction, 10 to the n over n factorial. Lots of stuff cancels here, right? Boop, boop, boop. N plus 1 over 10. It's the limit as n approaches infinity of n plus 1 over 10. Oh, shoot. I could have just done nth term test. Fell for my own trick. We know that factorials beat exponentials no matter what the base is. So function races, I could have said by nth term test, but I'm in it now. So anyway, the limit as n approaches infinity is infinity here, which is definitely a number bigger than 1, right? So I'm going to say diverges. It could have been nth term test, but I'm going to say by a ratio test. Or, ratio test, since I committed to the work. Oh, a big thing to the n power, I should try the nth root test. Take the nth root of that expression and just get the fraction. The nth root test is great because it's short. Got 1/2. 1/2 is less than 1. This behaves kind of like a geometric, so converges by the root test. The hardest part is figuring out which test to do. So it definitely, the best study thing I could say to do, if I'm a student doing this for the first time, is to look back through our homework assignments. This seems like a lot of work, but I would look back through the homework assignments and kind of classify problems. Like, all right, what did the problems look like where I did the ones that are harder are probably where I did integral test, or what did they look like when I used direct comparison or limit comparison? What did they look like when they were alternating, et cetera, et cetera? I would literally generate a list for myself and study what they looked like, because a lot of these tend to get recycled.